Luca, what kinds of tips do you have for building really, I guess we never know whether something is truly, the best that it can be, but how can we build um, more accurate or more efficient models in PyTorch? What kinds of tips and tricks do you have?
I don't have any unique tips and tricks. I'm just using whatever works. So I always start with a really simple way of thinking it. Okay, start with the simplest model and then build from there. You tend to think that overcomplicated models will work better, or because you have these easy tools that you need to put more layers, more different types of layers, or just number of layers, bigger networks, and stuff like that. And it does work sometimes, but if you didn't test much simpler models, then it comes to um, different comparison methods, and you can't get to the point of what actually is the bare minimum what works. So what is the baseline there? So start from there. And the other point is not my point, it's Ed Rang's point, that you have two ways of thinking about uh, implementing and optimizing your models. That is a model way or data way. So a lot of, especially beginners in this area, think about model way. So, okay, now I have an algorithm, it's not working properly. So what can I do with this? Can I increase the number of layers? Can I increase the complexity of single layer? Is the loss function the wrong one or hyperparameters one? All of the right questions, but you're not thinking about the data part. So sometimes your data is not right. So you can do and optimize your models as far as it can go, but sometimes you will go up to the ceiling and you will not be able to increase the accuracy of your models or the general performance of everything just by changing the model itself. So it's much easier to think about that because it's a couple of lines of code because of these libraries. But then, in most real world cases, collecting more data or relabeling something is the way to go. One of the projects where I worked in couple of years ago, we reached an amazing accuracy with the model that we designed ourselves. So fully custom model, it's a computer vision task. And then we reached a point of like 70-80% accuracy. And then researchers in my team, so I had a team of about 20 engineers that they led there. Um, and of course, they thought about, okay, can we implement better algorithm? Can we add more layers to it? And we did a lot of experiments there. But then a couple of engineers said, okay, but is the data part wrong in this case? And it turned out that 10% of our whole data set were wrongly labeled. So even if we increased the complexity of our layers or the models, we would reach the ceiling of, hey, but this is completely wrong. So what we want to predict is not aligned with what we have. So yeah, and sometimes the data view is much more safer and of course tedious, more tedious than just model one. But basically, going there that route is more safer in the long run, just to eliminate that and confirm, okay, the data part is correctly labeled. We can't, or why we can't reach more data points, and then start thinking about the model itself.
I see. Yeah, that makes a lot of sense. And then what about transfer learning? That could potentially allow us to
Of course.
take advantage of a more powerful model that was trained on more data than we have access to.
Yeah, for context for listeners that are not aware of the transfer learning part, transfer learning unlocked a lot of opportunities, and natively when you start thinking about it, it doesn't make sense, but it actually works. So what the transfer learning is basically large models that were trained by different companies like Google, Microsoft, Amazon, Facebook, or Meta. Like there are a lot of tasks and different models trained on those tasks. They invest millions of dollars just to get a small percentage better than their competitor, and to prove in some data set that they can do better, basically. But at the paper, it doesn't make sense. But for us, researchers or developers, makes a lot of sense because they invest a lot of money. So they train the model and they provide weights to those models. So it's trained on a certain task. Let's say a Coco data set, or let's say ImageNet. So it's completely open source data set on 1,000 classes. And now you have a specific task for your startup, for your company where you work, um, where you need to, let's say, make a classification between this pencil and this pencil for a factory. In the original way of thinking, you would need to collect thousands and thousands of different data points or samples depicting between these two types of samples. But that might be impossible, or you didn't have the time or resources. Because these companies train these large models, what you do is basically take those models, remove the last layer, and say, okay, now you start predicting binary classification between these two pencils. And you freeze the full network as except the last layer that you just added. So you're basically optimizing just the last part of the network, where the rest of the weights are optimized for the different data set. And that's why it doesn't make sense on paper, because it was trained on completely different task. But what they proved, that a lot of these weights are transferable and they can be used in many cases, and it actually works. So instead of collecting thousands, you can collect hundreds of images, and bam, it works like a charm. So in PyTorch and TensorFlow and other libraries, especially Hugging Face these days, you can import these big models in like a one line of code. And those models are really powerful, like for image classification, object detection, OCR, transfer learning for text these days because of LLMs. So you can do the transfer learning or basically any task that you can think of, and you have potentially a model built inside of these libraries, so you can just import it and start working from there.
Excellent. Yeah. So to kind of recap back to what you said there, we as machine learning practitioners, we can take advantage of these huge models trained on huge data sets that might have cost millions of dollars to train. In some cases, like the most extreme examples, like Llama 3 today at time of recording, they might have spent tens or hundreds of millions of dollars on this whole project to create these gigantic large language models trained on billions or trillions of tokens of pieces of natural language information from the public internet and also from maybe their own proprietary sources. And we can use things like Hugging Face, which you mentioned there, to easily download these model weights and then fine tune them to some specific task of ours. And then with some relatively small number of data points, like you mentioned, very commonly now just hundreds of data points, you can have an extremely high performing model in natural language processing and machine vision for some specific task that you want to have running for your business or your platform or some personal use case. And that fine tuning, because you're only fine tuning a small number of the model weights from the whole architecture, fine tuning on those hundreds of data points might cost tens of dollars or maybe even less. And you can have these really powerful models for very low cost.